Hello. All right. Welcome to this talk. So this is the topic of this presentation is CXL-enabled heterogeneous active memory tiering. My name is Bhushan Chitlur. I'm from Intel. I'm a systems data center systems architect. I focus on next generation data center architectures that includes heterogeneous accelerators, memory, as well as intelligent fabric. So this is a great segue into the prior talk because the prior talk focused on pooling, and this presentation hopefully motivates people to look beyond pooling to achieve better TCO. So I think many speakers in the past have. Oh, excuse me. Hi. I think the slide deck isn't showing up.
That's from my Alaska vacation. I actually took that picture.
Do you want to talk about that?
Yeah. Okay. Do you guys know why it's showing on here, but it's not showing over here? Let's see. There we go.
Awesome. So, all right. So I think like many speakers have spoken in the past today, right? There is a problem that has been recognized, and one of the most constrained resources in the data center is memory, and yet it is one of the underutilized elements in the data center. There's been a lot of analysis being done by universities as well as industry, and one such analysis was done by Meta. So and they published a really good paper called TMO, Transparent Memory Offload, in 2022, and so I captured some aspects from that paper and put it on the slide on the left here. So they pointed to two aspects. So first is this notion of underutilizing memory. So when an application or a VM requests a certain amount of memory, it does not actually use that whole amount. And so on an average, they said 50 to 60% is the amount that is being used, and the other 40% is just stranded memory. And like the prior speaker said, that stranded memory is not used by the application that requested it. Neither is it available for other applications to use, to improve their own performance. And so that is a total wasted resource. The second aspect that was highlighted in this paper is respect to cost. So if you look at a percentage of the overall infrastructure cost, the system memory cost is about a third, and it's expected to grow moving forward. And so this is a huge, you can think of it as a huge problem, but also an opportunity for us to look at how we can improve that. And they also looked at different types of memory, so compressed memory as well as SSDs. And the SSD line, is really good because it just is flatline across multiple generations, and it is also less than 3% of the overall cost. And so the thinking here is that can we leverage cheaper forms of memory, but yet achieve acceptable performance in order to achieve better TCO? That's sort of the problem statement of this presentation. On the right-hand side, you'll see the classical memory pyramid, where you want hot pages to be mapped to tiers of memory that are close to the CPU, and cold pages to be mapped to further tiers of memory. So given this sort of background, I want to sort of distinguish between two kinds of disaggregated memory topologies. So one is a centralized disaggregated pooling topology. I think the prior speaker spoke extensively regarding that. And another one is a disaggregated tiering topology. So disaggregated memory pooling is a great start. And I think in the past couple of years, it's been on many slides, and now we are actually seeing real implementations. So that's great progress. address. And in this topology, you essentially have a centralized pooled memory controller that is hooked up to multiple nodes. And that pooled memory controller manages that pool of memory connected behind it, and allocates and onlines and offlines, and enables the efficient sharing of that memory tier 2 in that left side picture. So I think this is a great start, and it does address some of the aspects with regards to underutilized memory. But it does not still address the fact of TCO, right? So it lowers TCO to some extent, but we are still using the same expensive memory that we would use on the local tiers. And so what the right side picture is trying to show is the use of different potentially cheaper forms of memory, and yet achieving acceptable performance. So on the right side picture, this is a memory tiering picture. So you have the tier 1 that is really the DDR connected to the CPU, and then you have the tier 2, which is CXL connected memory, and this is via a disaggregated memory controller. And then this disaggregated memory controller can implement behind it DDR, HBM, or memory semantic SSDs, or even SSDs with smart front ends. And this disaggregated memory controller can also have a remote connectivity to other remote memory nodes, or even other remote compute nodes that can offer memory to the overall pool. The point here, the point here is that the DDR that is part of this tier 2 of memory doesn't have to be the latest greatest, right? And you could use an older generation DDR if you want to, or you could even use SSDs and put the smarts in front of it in order to achieve acceptable performance. And we have had we have built multiple different prototypes to demonstrate the viability of this, and we see quite great promise in using this sort of heterogeneous memory for this kind of use case. So the local memory tier, or tier 2 memory, right? Even though it is physically local to the node, it is still shared amongst all the compute entities on that node. That means if you have a GPU or another accelerator, it can be used for that as part of system memory also. So all the memory that is sitting behind the CXL disaggregated memory controller shows up as a single NUMA node. It doesn't matter whether it is implemented via DDR, HBM, or SSDs, or it's over the network. It is still, shows up as a single system memory NUMA node, and it is that concept that allows you to seamlessly integrate different heterogeneous memory technologies without having the application or the host to know its exact implementation. So given this sort of a topology, right, now let's dig into one step deeper, right? So what is active memory tiering, right? So active memory tiering, again, is the ability to use cheaper, slower memory augmented with accelerator technologies to offset that slowness. And so what we're saying here is that you can use slower memory, but if you augment it with the right smart front end, then you can achieve acceptable performance. So you can view this architecture as sort of being made as 3 different layers. So one is memory side technologies. This is you can view them as almost like a physical layer that connects up to the different memory technologies themselves. So it could be DDR, HBM, or SSD, right? But given that these are slower memory technologies, you will need something in the front in order to offset that slowness. So in the case of SSDs, for example, right, you will need, of course, an NVMe host controller to talk to that SSD. But an SSD is a block device. A CPU makes requests as at cache line granularity. So what you would actually need to do is to build a module or functionality that first of all converts a cache line request to a block request. And because SSDs have this huge, microsecond, tens of microseconds of latency, you cannot expose that directly to an app. That does not work. And so what you would need to do is to build a caching layer, right? So you could build a cache in front of that SSD that allows you to read a block, cache it up front, and be able to, get order of magnitude better latencies for sequential accesses and even striding patterns. And this is stuff that we have actually built and demonstrated with internal prototypes. And we have seen some really encouraging results wherein even though SSDs have 10 microsecond latencies, when you run industry standard benchmarks like MLC and other memory characterization workloads, you can see sub half microsecond latency. So that's somewhere in the 500 nanosecond range, which becomes a very a practical way of implementing a tier 2 memory. So you could also use DDR and HBM, and you could build a cache. You can use the DDR and HBM itself as a cache for SSDs, or you could build an SRAM-based cache in front of this in order to hide some of that latencies. And the same is true for the remote connectivity as well. So the key here is that the memory side implementation is completely transparent to the host. You may have an NVMe host controller talking to SSDs, you may have a DDR controller, you may have an HBM controller, but none of it is actually visible to the host. This is it just shows up as a single pool of memory that is exposed via the CXL semantics and is used by an application as allocation from a single NUMA node, right? So once you have built out this layer that provides cache line granularity accesses, and you manage the heterogeneity of the memory technologies using in the device disaggregated memory controller device itself, then you can layer on top of it infrastructure services. And I think the prior speaker also mentioned a few of those, including memory memory health monitoring and detection and so forth. But in addition to that, you could do hot cold page detection. So this allows you to seamlessly migrate pages from the hot memory tier and the further cold memory tier, which is this the tier 2 memory. You could also implement things like data deduplication, compression, decompression, encryption, and even data replication. Right, all this can happen seamlessly on this device itself. And you could also implement workload specific accelerators specific to either AI or database on such a device. So if you layer the heterogeneous memory along with these accelerator technologies, all built as a CXL connected device to the host, then you will have some software touch points associated with the actual accelerator components, but not the heterogeneous memory itself. And so this sort of topology, we think, is very well suited to really drive TCO order of magnitude. And this is we have some point data associated with this, and part of the motivation of this talk is to get more people interested in exploring these sort of topologies in order to really drive TCO down order of magnitude when even compared to something like memory pooling, which is a great first step. So now, given that sort of an architecture that is very broad, has multiple different touch points, what kind of a platform do we think can support the implementation? So we propose an FPGA-based platform. FPGAs are really well suited for this sort of an application because they support multiple I/O standards, memory standards. So they support DDR, HBM, ability to implement NVMe host controllers on the device itself. They support, our latest, Agilex family of FPGAs supports CXL, by 16, and they support high-speed Ethernet. So this sort of a device is perfectly suited, not just from an interface perspective, but they can also implement the acceleration technologies that are required, and you could customize that, and you could actually evolve a portfolio of your own custom solutions in order to meet a certain class of workloads. So in addition to the Intel offering, there is also a rich ecosystem of partners who are building equivalent cards from that cater to this class of applications, and you can partner with them and start with evaluation, but go all the way to deployment at scale. So we're pretty excited about this whole ecosystem, as well as where this domain is moving. So last slide. So in summary, right? So we think this is the absolute best time to explore heterogeneous memory tiering. There is a great value prop and a great opportunity here for us to really lower the overall TCO value proposition. We think FPGAs are a great device for for the evaluation of this platform, and not just evaluation, but also a scale deployment of this. And the portfolio of technologies that you would actually need are many of which are already available. So it gives you a good head start to go off and evaluate, evaluate this sort of an architecture. There is a demo that we have, by UIUC in conjunction with Intel. So this is offloading of memory-intensive kernel features to a CXL Type 2 device. I encourage everyone to go in and speak to the folks there. It's a really good, excellent demo. So there are links here to our, the Agilex, our latest family of FPGAs, the Agilex 7 FPGAs, and also a link to the CXL IP for those of you who are interested. And we also have, I think, Pekan Gupta here in the audience. So if anybody is interested in, in learning more about the partner ecosystem, or need to get need to get more information on either our boards, our partner boards, or anything, please feel free to speak to Pekan. He's from our business unit, and he can help, facilitate those conversations moving forward. Thank you.